In this video, we're going to continue our discussion of inverse trig functions. So in the previous video, we talked about inverse sine, cosine, and tangent. In this video, it turns out we can also define inverse functions for secant, cosecant, and cotangent. So these will look pretty similar to their reciprocal counterparts, and it's very important that you understand the reciprocal identities from a few sections ago. So first we're going to talk about the inverse secant function. So you'll see this written as secant with the little -1 exponent of x, but remember that that -1 doesn't actually mean an exponent. So what we mean by that is the actual inverse of secant, not like 1 over secant, because we know that 1 over secant, so 1 over secant of x is just cosine of x. So the -1 is not an exponent. Okay, so the domain of secant of x is the absolute value of x greater than or equal to 1. So what this means is we can plug in any number that's bigger than 1, or we can plug in any number that's less than -1. And the range, so the answers that we get out are between 0 and pi. So 0 less than y less than pi, but we cannot have y equal to pi over 2. So if you remember, the graph of secant has an asymptote at x is equal to pi over 2, so it makes sense that in its inverse, we can't have a value at y equals pi over 2. And so just like we did with the other inverse trig functions, I'm just going to draw you a little picture so that you can remember where your answers should come from. So if this is our unit circle, that's 0, that's pi, and that's pi over 2. Our answers for inverse secant can come from the top half of the unit circle, excluding this point at pi over 2. So this is where your answers come from. So answers come from this half of the unit circle. So let's practice by finding some exact values. So in our first example, we have secant inverse of 1. So we can think about secant inverse of 1 as what angle has a secant value of 1. So that might be kind of hard to think about, so we can use our reciprocal identities to help us put it into a context we're more familiar with. So since secant is 1 over cosine, we can say that secant inverse of 1 is just the same as cosine inverse of 1, which turns out to be, so what angle has a cosine value that's equal to 1 and is in the top half of the unit circle? Well, we know that that's 0. Okay, let's look at another example. So here we have secant inverse of 1/2 is equal to something. So again, we want to word this to ourselves as which angle has a secant value of 1/2. Well, again, that might be kind of hard to think about, so let's rewrite it in terms of cosine. So we would be saying, since secant is the reciprocal of cosine, we would be saying which angle has a cosine value of the reciprocal of 1/2, which is 2. So secant inverse of 1/2 is the same as cosine inverse of 2. And that's kind of a problem, because if you remember from the previous video, we can't plug in numbers into cosine inverse that are bigger than 1. So cosine inverse of 2 is undefined. And that, again, comes from the fact that the biggest value of cosine we can achieve on the unit circle is 1. So we can't hope to find an angle with a cosine equal to 2. So that is the inverse secant function. Now let's look at the inverse cosecant function. So this one behaves very, very similarly, because remember that while secant is related to cosine, cosecant is related to sine. And so because sine and cosine are quite similar, secant and cosecant are quite similar as well. So once again, the inverse cosecant we write it like this. So we have CSC with that little exponent of -1, but again, doesn't mean an exponent, just indicates an inverse of x. So this domain is going to be exactly the same as secant. So our domain is the absolute value of x is greater than or equal to 1, and the range is going to be between -π/2 and π/2. So we have -π/2 less than or equal to y, less than or equal to π/2. But just like secant, there is one value we can't have. We cannot have y equal to 0. And once again, this is because on your cosecant graph, you would have a vertical asymptote at x is equal to 0. So for the inverse cosecant, we can't have a value at y is equal to 0. So once again, just to summarize this range, what we're looking at is the right half of the unit circle. So this is π/2, 0, -π/2, and your answers have to come from this half, excluding the point at 0. So this is where your answers come from. Okay, so just like with secant inverse, let's practice with some examples. So our first example is cosecant inverse of 2. So just like we did with secant, and we thought about it as cosine inverse, let's think about cosecant in terms of sine inverse. So the cosecant inverse of 2 is the same as sine inverse of 1/2. So now we need to think about which angle on the unit circle has a sine that's equal to 1/2. If you remember, our answers have to come from the right side of the unit circle. So the angle on the right side of the unit circle with a sine of 1/2 is π/6. So that's going to be our answer to the first one. And then the second one, we have cosecant inverse of 4/5. So once again, let's think about it in terms of sine. So if we translate this to a sine problem, we have sine inverse of 5/4. But just like in our previous example with secant inverse of 1/2 turning into cosine of 2, that fraction 5/4 is bigger than 1. And we can't hope to find an angle on the unit circle with a sine that's bigger than 1. So this is also undefined. And finally, let's look at the inverse cotangent function. So once again, we basically write this as cotangent with an exponent of -1. The domain for cotangent inverse is going to be all real numbers. So we can write this as -∞ less than x less than infinity, and that means all real numbers. But the range is going to be between 0 and pi, not including 0 nor pi. Okay, so what does this look like? Well, we have 0 and pi, and so this means our answers have to come from the top half of the unit circle, but there are no exclusions for specific values like there was for inverse secant, like how we excluded π/2. With this one, we don't have to exclude anything. So your answers should come from this half of the unit circle. All right, so let's try a couple of examples. So our first example is cotangent inverse of -√3. So just like with secant and cosecant, we know that cotangent is the reciprocal of tangent. So we want to take our cotangent problems and translate them into a tangent inverse problem. So if we want to translate cotangent inverse of -√3 into tangent inverse, we can say this is tangent inverse of -1 over the square root of 3. So now we need to think about what angle on the unit circle has a tangent value of -1 over root 3. And remember that this has to come from the top half. So we either need the first or second quadrant, and since our tangent value is negative, we know it must be an angle in the second quadrant. And we also know that 1 over the square root of 3 as a tangent value should give us some angle that's like pi over 6, but maybe some multiple of pi over 6. So the multiple of pi over 6 that is in the second quadrant is 5 pi over 6. So that is our answer for the first problem. For the second problem, we have cotangent inverse of 1. So again, let's translate this into tangent inverse. So cotangent inverse of 1 is the same as tangent inverse of 1. And so if you remember, for tangent inverse of 1, we need to think about what angle has a tangent value that's equal to 1. And if that's hard to remember, you can further think about dividing sine by cosine. So if sine divided by cosine is tangent and tangent is 1, that means that the sine value must be equal to the cosine value. And the only angle that this happens for is pi over 4. So that is our answer to cotangent inverse of 1. All right, so just like we did with with many of the sections we've done so far, we're going to briefly talk about how to use a calculator to evaluate some inverse secant, cotangent, and cosecant. So we're going to use a calculator to evaluate in radians rounded to 2 decimal places. So because it says in radians, remember to set your calculator to radian mode. So you should by now be used to switching your calculator back and forth, but I don't mind reminding you in these lectures. So make sure for these problems we're in radians. But other than that, we set it up very similarly to how we've been doing it by hand. It's just for that final step we use a calculator. So you probably noticed that your calculator does not have buttons for secant inverse, cotangent inverse, and cosecant inverse. So this is why we've been translating these problems into the 3 functions that we know really well. So we're going to do the same thing here, and then we're going to use the sine inverse, cosine inverse, or tangent inverse button to actually evaluate these. So secant inverse of 3, if we translate that into cosine, would be cosine inverse of 1/3. Now at this point we can actually use our calculator, and when you type this in you should get 1.23 radians. Okay, next example is cotangent inverse of 1/2. So once again, we want to translate it to tangent inverse. So we have tangent inverse of 2, and if we type that into our calculator, we should get 1.11. And finally, cosecant inverse of -4, we can translate into sine inverse of -1/4, which if we type that in, we should get -0.25. All right, so that's basically how to use a calculator for these types of problems, but remember, I only want you to use a calculator if I tell you to. Okay, most of these problems will be done by hand, and probably all of the problems on your test I'm going to require exact answers, which means you won't be rounding. But for some of your homework, I do think it is important you know how to use a calculator for word problems and the like. Okay, finally we're going to look at some problems that are very similar to the stuff we did towards the middle to end of the inverse sine, cosine, and tangent section, which was the previous video. So you remember those problems where we had sort of like one trig function plugged into another trig function, and that's exactly what we're going to do now. Except now we can also include secant, cosecant, and cotangent, and furthermore, we're going to switch around the ordering of some of these things. So if you look at this first example, this one looks very similar to the ones we did in the previous video. We had an inverse function on the inside, and we had a regular function on the outside. But notice in these last two, we switch it up. So we put the regular function inside and the inverse function outside. So that's going to be worked a little bit differently, but we're going to get to that. So in this first example, we have cosecant of tangent inverse of 1. So the most important thing to remember is just to work these from the inside out. So the first thing we're going to look at is tangent inverse of 1. Now, We talked about cotangent inverse of 1 just a second ago, up there in our examples, and we said that was the same thing as tangent inverse of 1, but we're going to go over it again. So tangent inverse of 1, we want to think about which angle on the unit circle has a tangent value of 1. Well, that's going to be pi over 4. So this is going to become cosecant of pi over 4. Okay, now our job is to evaluate cosecant of pi over 4. Well, we can use our reciprocal identities to make it a little bit easier. So cosecant is the same thing as 1 over sine, so we're going to have 1 over the sine of pi over 4, which is the same as 1 divided by the square root of 2 over 2, which is 2 over the square root of 2, which is just the square root of 2. So cosecant of tangent inverse of 1 is the square root of 2. So like I said, pretty similar to the stuff that we did in the previous video, except we could have cosecant, cotangent, and secant in those outer functions. And just remember, if you don't have a unit circle value on the inside, you will have to draw the triangle, and I believe we did that in a couple of the examples in the previous video. Okay, let's look at cosine inverse of sine of 5 pi over 4. So like I said before, this one's a little different than all the ones we've done so far because we have the inverse function on the outside and the regular function on the inside. So the first thing we're going to do though is just work it from inside to outside. So we're going to evaluate sine of 5 pi over 4 first. So let's think about where this is on the unit circle. So 5 pi over 4 is 1 pi over 4 more than pi. So if this is pi and this is 0, then 5 pi over 4 must be right here, right in the middle of the third quadrant. Okay, so the sine of 5 pi over 4 is going to be negative root 2 over 2. So our problem becomes cosine inverse of negative square root of 2 over 2. Okay, so this is where the problem gets a little tricky because we have to remember which part of the unit circle our answers can come from. So for cosine inverse, our answers have to come from the top half. So what we want is which angle in the top half of the unit circle has a cosine of negative root 2 over 2. So we know it must be in quadrant 2 because that's the only one out of quadrant 1 and quadrant 2 that we could end up with a negative cosine value. And furthermore, we know that this must be the angle with a denominator of 4 in quadrant 2 because we have root 2 over 2. So that angle is going to be 3 pi over 4, and so that is going to be our answer to this problem. All right, let's look at our last example. So this one's pretty similar. We have an inverse function outside, a regular function inside, but that regular function on the inside is what we're going to work first. So we're going to look at that first. All right, so let's think about where negative 7 pi over 6 is. So remember, with negative angles, we count backwards, so clockwise from 0. So at negative 6 pi over 6, that would be the same thing as pi. So negative 7 pi over 6 is going to be 1 pi over 6 past pi. So this is negative 7 pi over 6. So the cosine there has to be root 3, or negative root 3 over 2. So we have sine inverse of negative square root of 3 over 2. And now let's remember what sine inverse forces us to take our answers from. So sine inverse, we have to take our answers from the right half of the unit circle, and we want the angle in that right half that has a sine value equal to negative root 3 over 2. Well, the angle must be in quadrant 4 because that's the only quadrant that we can get negative sine values in. And if the sine is negative root 3 over 2, well, it must be this negative pi over 3 angle down here. Remember that sine inverse goes between negative pi over 2 and pi over 2. So we always want to call that angle in the fourth quadrant negative pi over 3 rather than counting all the way around counterclockwise from 0. So this answer is going to be negative pi over 3. All right, and that concludes our lesson on inverse trig functions.